Hi, this is Professor Fernandez, and we're working on Class Notes A in Lesson 9. So the point of this example is to help us motivate the introduction of the determinant. And I'm going to do that by looking at this system, two equations and two unknowns, and examining what role this quantity, AD minus BC, plays. So we can see here that the first objective is to show that if this quantity is non-zero, then this system, this 2 by 2 system, has a unique solution, and it's given by this. All right. So as a preview, right, what does this all imply? Well, this quantity shows up in the denominator. Okay, so that's something that we'll see later on in these lesson notes. Has to do with Cramer's rule up here. Okay, it also tells us that, excuse me, if this quantity is non-zero, then I can actually find the solution xy, and it's unique. So that's, again, another preview of the importance of this quantity. And, last preview, I suppose, AD minus BC is the determinant of the coefficient matrix in this system. So this is all to motivate that concept and certainly Cramer's rule later on. Okay, so let's work out the first part of this example. So what am I going to do? I am going to effectively use row operations to solve this system, like we've been doing in the previous lessons. But I'm going to do it from up here first. So first thing I'm going to do is multiply this first equation by d, the number d, this one down here. And then I'm going to multiply the second equation by the number minus b. Okay, so b like this number, except with a minus sign in front of it. All right, so what's going to happen? So the first equation is becomes a dx plus b dy equals dr1. The second equation becomes minus bcx minus b dy equals minus br2. And then you can kind of see why I've done this down here, because now I'm going to add these two equations. And I have b dy minus b dy, so those terms cancel. And what am I left with? I'm left with a dx minus bcx equals dr1 minus br2. I can factor out the x from the left-hand side to leave me with AD minus BC times x equals dr1 minus br2. Great. And then I can divide by x. Again, I'm assuming that AD minus BC is non-zero, and that's why I can divide by it. All right. So I'll come back here in a minute after we have found the y and make some comments about that. But you can see that this thing that I've boxed matches what we got over here, right? dr1 minus br2, the numerator, divided by AD minus BC. So we have found the x value, again, assuming that AD minus BC was non-zero, because here it was, and I had to divide by it. Okay. So how do I find the y value? Well, I have the x value, and then I can go back to any one of these equations up here and then just plug in the x value. I'm going to do that over here, the second equation. So I'm going to scroll down a little bit, and I'm going to say cx plus dy. I'm just writing the equation to remind myself what this is, equals r2. So I'm going to plug in the x here, dr1 minus br2 over AD minus BC plus dy equals r2. And then my objective is to solve for y. So I'm going to move this entire thing to the right-hand side and keep the dy over here. So r2 minus this glob of stuff. And at this point, you might be getting a little nervous that there's a lot of stuff going on, but that's okay. We will simplify things as we go. And then I'm going to divide by d. And then this should make you even more nervous. There's a bunch of letters and floating around, and that's okay. We will take this step by step. Okay, so let me move all of this over. Let's see if it will work out like I want it to. Okay, perfect. So I'm going to put it over here. And let's start simplifying. So first thing I'll do is I will find a common denominator, and that's AD minus BC. All right. And this is R2 divided by 1 here. So when I find a common denominator, I will multiply this 1 by AD minus BC, also multiply the numerator by AD minus BC. Great. So that's going to give me an R2 times AD minus BC here. And then I have this term left over, minus C times that. So minus C times dr1 minus br2. See, so we're already making progress, and we will keep going. So I will leave the denominator, AD minus BC, and then we're just going to start multiplying things out here. One thing I'll mention, it is always useful to have a sense of where you're heading. So let's scroll up a little bit. And we want to show that the solution for y looks like this, right? So this is kind of the numerator we're aiming for, an AR2 minus CR1. So that's always helpful if you know what you're aiming for. So AR2. So we see that term here. Let me put it in red. Here is an AR2, and here is a minus BR2. Okay, so we're heading in the right direction. Great. So let's continue multiplying things out here. So I get D times AR2, okay, that's this first term, minus BCR2, and then minus DCR1 plus BCR2. So I've multiplied out the numerator. And you'll notice that this term BCR2 cancels out, BCR2. Great, so what am I left with? I am left with 1 over D times D AR2 minus D CR1 all over AD minus BC. Great, so I can factor out this D here and cancel it out with that one. Okay, so this goes away. That assumes that D is non-zero. So that is an additional assumption that we are making here in this problem, at least the way that I have chosen to solve it. It turns out not to be an assumption that's needed if you solve this a different way, but I've done it this way to be as transparent and connect to what you might do, which is exactly what I did, solve for y and then substitute in the x value. So we could have done things a bit more generally, but that might have caused a little bit of confusion, so I chose this route. So we have arrived at the y solution for this problem. So let me go back. I had said a few minutes ago to add some context and some insight into what has happened. So we got the y solution, great, and then we also got the x solution from before. Sounds good. So what more do I want to say, right? So notice that back here, AD minus BC, we needed that to be non-zero in order to divide and solve for x. So that explains why this is here. Now notice what might happen. Let's suppose that this is 0, right? If this is 0, then this equation here would be 0 equals this right-hand side. So you can kind of foresee the other two solution categories we've been talking about for linear systems coming up. If this quantity over here if this quantity over here is 0, then that will be fine because you'll get 0 equals 0. Sure. But if this quantity over here is non-zero, then that will not be fine because you'll get 0 equals whatever the number is, 7 or something, and then you'll get no solution. Okay, so my only point in bringing that up was to foreshadow for you the fact that we'll learn later in the course that if AD minus BC for the system is 0, then sometimes you will get no solution, sometimes you will get what are effectively infinitely many solutions, right? And we saw that example in the previous lesson in the last example. Okay, so we have done the first part of this example. Let's now talk about the second part. And this is, the massive amount of foreshadowing that I was just doing. So show that when the AD minus BC equals 0, the system has either no solution or infinitely many solutions. And find the conditions on the parameters that lead to each of these cases. Great. So we've done a little bit of that work already, right? So I'm going to scroll down a bit here to number 2. So if AD minus BC equals 0, then, as we just saw, AD minus BC times X equals dr1 minus br2. Great. Let me finish this sentence. If AD minus BC equals 0, then this equation implies that 0 equals dr1 minus br2. Okay, and this is kind of as far as I want to take it. From here, if dr1 minus br2 is 0, then the system has infinitely many solutions. Why would that be? Well, that would be because if this right-hand side equals 0, then one of the reduced equations in the original system is essentially 0 equals 0. And there will remain the second equation. Okay, so whatever form of an equation this looks like, again, because we're in just the plane x and y variables, its graph will be a line. You know, it could be a line that looks, you know, slopes this way, slopes that way, whatever. But it'll be a system of two equations, one of which literally contributes absolutely nothing, and then a line. Okay, so there are an infinite number of points on the line, so you will get an infinite number of solutions. So that's one thing that could happen if this condition down here that we have just described is true, if this is 0. Okay, so what about if it's not 0? So I will sort of write up here since I ran out of space. If not, i.e. if dr minus br2 is not 0, then I'm going to say star, which is this whole condition above star, is violated. And so there are no solutions. Okay, so that's what we were talking about a minute ago, that if I, in the course of doing my row operations, get to here, and the left-hand side is 0, but the right-hand side is not 0, then I will have 0 equals some non-zero number, right? Some non-zero number, which is not true. So there's no way that I can have a solution for the system in that setting. Okay, so we are done with this example, and I just want to scroll up since we've done a lot, remind you of the main takeaways. So takeaway number 1 is that it appears that when we solve a system of two equations and two unknowns, this specific quantity, AD minus BC, really tells us a lot. If it's non-zero, it tells us that the system has a unique solution, and moreover, in that case, the actual solution has that quantity in the denominator, right? So heightening its importance. When that quantity equals 0, then the system does not have a unique solution. Instead, it throws us into the other two categories that we've been talking about for solving linear systems: no solution or infinitely many solutions. We talked about, just a minute ago, an additional condition for these types of systems that can distinguish these two cases, right? But distinguishing if which one of those two cases is true in this setting is another thing that we're going to talk about later in the course.